As Filippo mentioned, I only learned I was speaking a few hours ago, so apologies if this is not my most polished delivery, and you're getting a recycled talk from last year. This is a talk that my coworker Rob Findley and I gave in New York last summer to describe the work we did together to redesign the core of Gopls to make it use much less memory and to scale to much larger projects. I just want to see a show of hands. Who here has heard of Gopls? Oh, good number. Okay. And how many of you use Gopls? Well, similar number. All right. Good. Okay. So possible selection bias, of course, because it's in the title of this talk. But anyway, so when you use a traditional IDE such as IntelliJ or GoLand, it combines an editor and all the analysis tools that you need for a given language. Whereas by contrast, Microsoft's Visual Studio Code, VS Code, shown here, took a different and unusual approach in its design, and it split these two roles, moving the analysis into a language server, which is a program that runs alongside the editor. And the two programs communicate over a network connection using the language server protocol, or LSP. And the nice thing about this design is that the editor can work with any language server, and the language server can work with any editor, even Stone Age tools like Emacs, which is what I use. And so Gopls is the language server protocol server, or language server for Go, and it's maintained by our team in New York. Now, in 2022, we were very concerned about the performance of Gopls. This slide, in particular, the first 3 lines on this slide, highlights the problem. First of all, it was very slow to start. It took minutes in some cases. And it was just as slow to restart after a crash, and it was crashing quite often. The second problem is that it used a lot of memory. Many gigabytes was typical, and in some cases, many tens of gigabytes. And it often took a long time just to deal with the fact that you were typing. Like, you type a letter, and it would respond in about 67 milliseconds. And if you're a good typist, that's pretty close to sort of not really keeping up with your typing speed. And so we really had to admire the patience of some users who would put up with numbers like this and yet continue to use the product. And perhaps that's because the numbers are worst when navigating the very large projects, but that's exactly where you need tools like Gopls the most. So why did it take Gopls so long to start? Why did it use so much memory? And why was it so slow to respond? The fundamental answer to all 3 of these questions is that Gopls used to build a single large interlinked data structure representing the entire program in your workspace. It's sort of analogous to what would happen if you tried to compile your entire project in one gulp. This picture, which we'll return to throughout the talk, represents a directed acyclic graph, or DAG, of packages. The downward arrows represent imports. The arrow points from A to B because A imports B. Each package defines a set of symbols, such as imported package names, constants, variables, types, and functions. Gopls is built on standard packages in the standard library, like GoAST for the syntax tree and GoTypes for the type checking. And these together work like the front end of a compiler. So each of these green nodes represents a list of parsed and type-checked and type-annotated syntax trees. And these are large data structures. Typically, they're about 30 times larger than the source code that they came from. Now, the usual discipline in a compiler is called symbolic programming. This is the idea that you create exactly one data structure, called a symbol, to represent each function, type, constant, or variable. And then you refer to this symbol using a pointer every time you need to refer to it. At that point, the names no longer matter. Just the pointers are all that matters. The names have been sort of melted away. Pointers are very compact, and you can very quickly compare 2 of them. It's just a single machine instruction to compare. And so it's a very efficient representation. So we'll use the find references operation as a running example. So it returns the location of all the references to a selected symbol. Gopls used to simply locate the target symbol, then scan this big data structure for all the pointers to it. Let's say the target symbol is in package B here in red. If the symbol is unexported, so it has a lowercase name, then we only need to search within the package B itself, so it's very quick. If it's an exported symbol, we need to look further. We need to look, if it's a package level symbol like func, var, const, type, we need to search for all the packages immediately above A, immediately above B, such as A, because A has to directly import B in order to use its package level symbols. But for an exported field or method, you actually need to search all the way upwards. You need to search for any package indirectly above it that transitively imports it, because you don't need to import a package to use its methods or fields. So either way, this gives us a set of packages we need to inspect. So then we scan the syntax trees of those packages, looking for pointers to the target symbol, and that's basically all you need to do in the old way that Gopls used to find references. The query was simple and fast. But here's the problem. The symbolic programming approach works great for one package at a time, but in Gopls, the entire project was loaded in this way as a large, tightly interconnected web of pointers. Each time we type a letter into a file, we need to replace its node. But we can't replace a single node in this graph without destroying and recreating all the data structures above it in this big graph. So to make this efficient, we would have to drastically redesign the model. Now, it turns out there is a standard technique for doing this, and it's not new. Since the 1950s, people have wanted to compile programs that were too big to be held in memory all at once. The solution was to break the program into units and compile them separately, finally joining them together in the linker. This picture is an IBM 704, the first real mainframe computer, and its Fortran 2 implementation was the first to pioneer this concept. But back then, it was the programmer's responsibility to make sure that all the parts of the program were consistent with each other. For example, if one part of the program treats global variable v as an integer, then all the other parts of the program had better do so as well. It wasn't until much later, in the 1970s, that compilers would export a summary of what they had learned from processing one unit that they would then read again when they analyze a later unit. And that way, consistent type information could propagate upwards through the graph during the build. Now, the Go compiler does exactly this for type information, which it emits in the form of export data. Each package on the left is replaced by a compact summary on the right. This is a serializable summary, which something we could write down efficiently. And each time the compiler needs to re-import package P, it just reads the summary on the right. The type syntax trees for P, the big complex data structures, are not needed. So our first step was to apply this technique to Gopls for type information. We reuse essentially the same export data format and algorithms as the compiler does, but with one difference. The compiler's summary includes not just the package members, but also any types that are from other packages that are indirectly reachable through those fields and methods. We call this deep export data. And the nice thing about using deep export data in the build is that it means that you only need to load exactly one summary file for each of your direct imports. The problem is that we found in Gopls is that a few very large types, like there's a one big package in Kubernetes, for example, that just declares all their API types. And everything essentially makes use of some of those types. So you find that you're using the same types indirectly over and over and over again from every package in this big workspace. And so we found a case where the indirect data that you were loading was from all of these deep export data files, was about 300 times larger than the direct data. So it just doesn't scale. So Gopls uses shallow export data. Each package records only its own information, and you may have to access sort of some subset of the forward transitive closure of your dependencies during type checking in order to get fields and methods. But nonetheless, you typically need only a small number of those, so it was a big saving. And in fact, we may consider doing something like this during the builds too. So export data solves the problem of summaries for types, but it doesn't include all the other information that Gopls might need to respond to typical LSP queries. So some operations, like to hover over a symbol and see information about it, or to jump to a definition, those are actually quite simple because they need information only about the local package in which the symbol is declared. But other operations, like searching for symbols throughout your workspace, the search index, or to find all the implementations of an interface in your workspace, they potentially have to globally search the entire workspace, all the packages in the workspace modules. And some of these operations run on every keystroke, like the reporting of compiler diagnostics and other diagnostics. And while others, like renaming a symbol, these things are triggered only by explicit user actions. Previously, we didn't have to think about these differences because this big monolithic data structure could sort of take care of anything we needed to ask it, even though it was inefficient to recompute it. But in order to break this structure down, we needed to sort of work backwards from the specific needs of the operations we had and to build custom optimizations for each one. And we need to build a serializable summary of the indexes we need for each of these operations. So using export data means that we can type check each package independently. But then we no longer have this pointer relationship between symbols. So in this picture here, the data structure representing a symbol in A will not be, the data structure representing a symbol in B will not be the exact same data structure seen when we import B when we type check package A. There'll be two separate variables that represent the same thing. So we can't just compare pointers anymore. Instead, we need to use a naming scheme. And so for this, we invented a thing called an object path, which is really a naming scheme or a string that can describe any exported symbol. So here's one illustration. I'm not going to go into all the technical details, but here we are trying to construct an object path, the name, that represents this thing x on the screen, which is a field in a struct returned by a function, a method. So the object path algorithm identifies it as the first field of the second result of the first method of the underlying type of the name t. I don't expect you to memorize that. The point is simply that an object path is a stable name for a symbol relative to its package. And unlike pointers, these names retain their meaning when they're passed between processes through the file system, for example. So these names are fit to be saved in a persistent index. I'm going to skip the next detail just to save time. So each time a package has changed, we type check it again, and then we recompute the index of cross-references and all the other indexes that we need, and then we can actually evict the type syntax trees from memory. So this is a big memory saving. And then when we later need to query the references from, to a symbol in B, if we make a cache hit in this index that we produced earlier for B, we can avoid actually thinking about the type checker data structures and avoid recomputing them, and just serve the result from this index. So after change to package A, such as an editor keystroke, we need to retype check A and all of its importers, the nodes above it, which are in blue. But we can leave the white nodes alone because they haven't changed. So in other words, it's an incremental build. Now, after a process restart, like either you just went home for the day and the thing timed out, or the process died because of a crash, if we haven't changed any files, then this index that we computed is still valid. So we can serve a references query again the next day without type checking anything. But on the other hand, what if there are no indexes, such as the first time we open up the project? Or if we must recompute everything after a change to a very low-level package? This sort of, at that point, still degenerates into the original algorithm, where we have to type check everything all over again. And the answer is, well, yeah, it is expensive in that case. However, yeah, there's really no getting around the need to retype check everything after a low-level change. But the way that we were doing before was this sort of top-down approach, where you would, for each node, you would bring its dependencies up to date in parallel, and then process the node itself. And the lazy way to write this sort of thing is that you start at the top, node number 6 here, and then you say, first do the dependencies, 1 and 5. And then the process repeats at number 5, and you say, OK, first do the dependencies, 4 and 4 on this one, and so on. And this means you've sort of started 6, and you've started 5, and then you started the 2 nodes numbered 4, and so on. You've started all this work before you've really, so you've got all this unfinished work before you actually get anything done. And it turns out this is actually a really inefficient way to do it, because it creates a lot of Go routines for all these edges you can see here, and it starts a lot of work before it finishes anything. And so it creates a lot of contention, creates a lot of concurrency that is not really helping. It also does repeat work for each of the edges in this graph, because it's not really planning as a group all of these operations. And so the much better way to do this is a two-pass thing, where you analyze the whole graph and see what needs to get done, and then you work from the bottom upwards. And then you can still do it in parallel, but you can reduce the number of times you visit a node because you have multiple edges to it. And so as soon as you've finished a node like these nodes in level 1 at the bottom of the graph, as soon as you've finished all those things and you've produced their summaries, you can actually just evict all those things from memory, and then you can start processing 2 and nodes in level 2 and work up that way, and so on. So this actually reduces the amount of live memory, and it reduces contention, and it is better for CPU. So at each step, GoPlease is producing a summary of the package type information to keep around for the next layer up in this graph. And I think there's a nice little generic utility to write out of this, because it's a thing that comes up a lot in our kind of work. So let's now look at the structure of the index. So for cross-references from one package to another, we need to build a special kind of index. And the code here shows you a small program that refers to 3 symbols from another package. There's functprint, there's os.stodout, and there's the write string method. For each reference to these symbols, we record 4 pieces of information. We need to know the start and end location of the reference, each of which is a file line column triple. We need to know the path of the package that defines the symbol, and we need to know the stable name, the object path of that symbol within its package. And I've sort of fudged the notation here a bit for clarity, but this is approximately how it is. And we build this index for all of the cross-package references. We don't need to do it within the package, because we're always going to type check one package, the one that defines the symbol, but it's all the references from other packages for which we need the index. So, so the goal is, so if we gather up all these references, we basically have a set of sort of 4 tuples of start, end, package path, object path. And this is kind of a relation in a relational database, if you like. And this table of these tuples forms the index. So obviously there's lots of redundancy here, like lots of file names are the same, lots of tuples share fields in common. There may be many calls to functprint, so we don't need to produce the same strings for those names over and over again. So there's a lot of actual compression within that table, but conceptually it's this sort of row of tuples. Anyway, so this tuple becomes a binary encoding, a blob of data, and as is always typical in this kind of work, the graph looks like this. Everything is small except a few things which are enormous. So these are the sizes we deal with, a few megabytes at worst. So that was the index of cross-references. There's a second index here. There's several of these indexes. I'm not going to go into all of them, but I'll give you a second one just to show you the pattern. This one is the index of method cross-references. So as you know, in Go, there is no explicit relationship between a concrete type and the interface that it implements. Any type that has a string method is a stringer. Any type with a read method is a reader. So when you ask your editor which concrete types satisfy this interface, it has to really, or the inverse question, it really has to do a lot of subset tests to say, does this concrete type's set of methods, is it a superset of the set of methods of this interface? And just keep asking for every candidate type, is this subset relationship, does it hold? And it could be a lot of types, because it has to potentially search for the entire workspace. So we build this method set index for a package in a similar way. And again, it produces tuples. The only really interesting detail here is that we produce this string called a fingerprint. And the fingerprint is a sort of canonical way to render the name and the type of a method as a string, with this very special property that if two fingerprints are equal, the methods are identical as defined by the Go spec. And so this lets us implement the interface satisfaction check as essentially a bunch of string subset checks. There's more complexity here we don't know how to do yet, even for some corner cases of generics, so I'm not going to go into the details. But again, this produces a tuple and then a row of tuples that we then compress as binary into a store. So let's look at where we store the data. The answer is, in short, in the file system. This slide shows the API of Gopls' file cache package. It's just about the simplest imaginable persistent key value store. It has just two methods, set and get. Like a build system, the cache records facts of the form, if you follow this recipe, you get this cake. Both the recipe and the cake can be quite large, hundreds of kilobytes, maybe in megabytes. And so we use a cryptographic hash of the recipe as the key, and we also use a string, like in this case, bake, to sort of segment the different portions of the cache for different purposes. So as soon as you know the recipe, you call get. If someone has baked this exact recipe before, you get a cache hit for that cake. But if not, or if the recipe or ingredients have changed by even a single bit, it's back to the kitchen, you make a cache miss, you do some computation, some baking. Once you finish baking, you call set and you update the cache. So a recipe, you can think of it as an operation plus its arguments, like compute the prime factors of this number. Or a more realistic example is compute type information for this package with these source files and these dependencies. And we use content hashes to identify the source files and recipe hashes recursively for the dependencies. And in this way, we account for the entire set of dependencies all the way down to the very bottom. Like a database, the interface is atomic. If two threads race to bake the same cake, that's fine. One will win, the other will lose, but the effect is going to be the same. It's not a content addressable store. The key is the hash of the recipe, not the actual value. Otherwise, you couldn't make a cache hit without baking the cake, which sort of defeat the point. I'm going to talk very quickly about the implementation of this cache. It's a global persistent store. That means there's one per user and machine pair. They really are global functions. And these caches live across process restarts and handle multi-process concurrent access. You can think of it as basically a relational database, but we couldn't use a database because we are very strict about dependencies in the golang.org/x repos. So we have to use the file system. I'm going to skip this slide because I'm running short on time. But I wanted to mention that building this tiny little database, you think that the right way to do it would be to use atomic rename in order to achieve atomicity in the file system. And that's the classic Unix solution. And it works great on Linux and other Unix systems because POSIX guarantees that the renames are atomic. But it just isn't portable. Like, there's just simply no way to do this on Windows. There are lots and lots of ways that look like they should work on Windows, but there is no way to rename a file or directory atomically on Windows. And so the next thing we looked at was to use file locking, which is this famous set of problematic Unix system calls. They say locking. That sounds like it should be the right kind of technology. But it's always been a notoriously unportable and tricky and buggy operation on the Unix platforms that have it. We tried this for a little bit, but we just found that we were just endlessly getting all kinds of kind of unpredictable, flaky bugs. So we again rejected this solution. I don't think file locking has really worked very reliably for anyone in all the years I've been exposed to it. So the solution we ended up using was actually thanks to Russ, who pointed me at this very simple thing he'd come up with for the use in Go build, which is that he observed that no file system guarantees that concurrent file writes are atomic. However, every file system actually behaves in this way and must behave this way for reasons. And so if you write small disk blocks, like no bigger than half a kilobyte, for example, there's simply no way that two concurrent writes can produce anything other than atomic behavior. And so the trick is to sort of produce a level of indirection where we put file contents in a content addressable store where the name represents the file contents, and you can race all you like on that because you're always writing the same bits. And then you use this atomicity property for very short files to write down a kind of link that, that lets you update the cache. Again, I'm running short on time, so I'm going to skip through this. But the point I'm trying to get to here is that this piece of code that's like about 100 lines long turned out to be a nice atomic files key value store that's been completely problem-free since we built it. No need for a database, and it performs just fine. And it's used in GoBuild for the cache of GoBuild. So now let's talk about what happens when a change comes in. So look at this yellow node. We don't need to invalidate and recompute every node upwards in the graph. Only the upward dependencies. And this is not a new observation. This is what it means to do an incremental build. It's just like what Make did in the 1970s and every build system since then. Now, Make uses timestamps because it wants to maintain the invariant that newer things point to older things, as it were. So if the yellow node is changed, then there's work to be done to recompute these sort of purple nodes above it in the graph. And if the yellow node changed again back to the way it was, then again you have to recompute those purple nodes again. So this is what GoPlease has always done. So every time you change a file and change it back, you sort of recompute things twice. But newer build systems don't work this way. Vesta from DEC and Bazel from Google and GoBuild now actually use this. They don't use timestamps. They don't blindly throw away old work just because a dependency became newer. Instead, they ask, have we done this requested task before? And have we baked this recipe before? And if the answer is yes, then we can still make a cache hit. So consider a small local change to a package, like the addition of a print statement. Clearly, the yellow node needs to be recomputed since it changed. But what about the packages above it? Now, their source files haven't changed, nor has the summary of the export data, the types coming out of the package that did change, because we didn't change the signature of function A here. So when we look at the nodes above A, we can make cache hits for those things because the recipe is the same as it was before. And so if you can define the recipe precisely without irrelevant ingredients like the sort of content of function A, then we're able to make cache hits when only the irrelevant parts change. So I'm going to skip again forward here. So here there's just an example of a slightly more substantial change. We changed the signature of function A to add a parameter. Now, the type summary of this package has changed, and we have to recompute the packages directly above that, the ones that import it directly. But probably they didn't change in any material way because of this, and so the things that are now indirectly above that don't need to be recomputed. So we can prune the scope of the effects of this change. So this is a way in which we reduce most of the work of typical changes that you make when you're editing your source code. I'm going to skip this slide just because I think we're short on time. And I'm going to give you just one hint of one of the other algorithms we use here, which is that we are able to do this kind of fine-grained tracking of dependencies, not just at package level, but at symbol level. So we actually do a pass over the syntax trees, trying to find, at the level of individual functions and types, what references exist from one symbol to another. And so in this case, you have an idealization of the fumped package, and you can see that the printf function depends on a blob of stuff that depends on quote, parsefloat, and new, and scanf depends on a different blob of stuff, depends on like some of the same things and some other things. And for every package, we produce this kind of summary of this blue sort of graph of what depends on what. And then we're able to sort of stack these little summaries together and then trace paths through this graph so that you can see that when a package like sync changes, naively you would think, well, sync is used by fumped, and fumped is used by log, and that's used by main, so if sync changes, main has to change. But we're actually able to trace through the symbols that main uses from these packages and realize that there is no path from main through a path of symbols to sync. And so when sync changes, it doesn't actually matter for this program. So again, we're able to reduce the number of recomputations we do. So there's a lot more detail here. I'm not going to go into it because we're about out of time. Again, this is more detail. I'm going to just skip forward to this, which is a sort of summary from a year ago. The overall gains we got here were much faster startup, down from like minutes in some cases to mere seconds, much smaller memory usage, a slightly higher cost of bookkeeping after each keystroke, though the numbers are way better than they originally were by now because we spent the last year doing further optimization work. And at that time, also query latency was unchanged, although it's now actually also much faster. So the GoPlease 0.17 release is coming out this month. We'll have a pre-release hopefully later this week. There's a lot more of these optimizations in it, and we'd really appreciate it if you would try it out and let us know what you think. I'm just going to show you one graph here that just shows you that this is not just a multiplicative change to the performance, but it's really an asymptotic change. In other words, the bigger the project is and the worse things were, and the more the benefit you will notice. So as the repositories get larger, the relative savings get even larger. And so you can see in the best cases, the very largest projects, where you most need tools like GoPlease to help you navigate your way around, we're getting savings of over 10x performance improvement. So I think I'm out of time right now. I'll stop there. One more minute. OK, I'm happy to take questions from anyone. So, yeah.
Microphone coming.
Hello, thank you for the talk. I have a question. When I use GoPlease and I go to a reference to the standard library to see how, for example, sync works, I believe GoPlease stops working there, and I cannot go to more references. And if I try to modify Go source code and like make GoPlease work with that, it doesn't work. Why is that? And if maybe it will be fixed?
So if the source of the standard library you're using is the same place where the Go command is, in other words, you're looking at the same Go root installation as you're actually using on the Go command on your path, it should work. If the problem is when you have like user local Go or something or other, is the actual Go toolchain you're using, and you have in your home directory some source trees for the standard library. When there's two of them, it will not make the connection. It would be nice to fix that. It's quite tricky to fix it. But if you're using only one installation for your source and for your actual Go binary, it should work.
The less simplified example is the module cache. If you go to a third-party import of yours and you land in the module cache, GoPlease definitely stops working.
Still?
I don't know about still.
I think
on my computer
that was the zero config.
Okay, maybe I should update. But
then.
yeah, like it would navigate and then. It doesn't work. Oh, good.
Yeah.
Thanks. So maybe you should update too.
Another question. Sure.
So sometimes when you're editing code, you have like invalid state, so you're still pressing, or like you're implementing an interface and you haven't done all the methods yet. And it seems to me that GoPlease seems mostly work, even though the Go compiler would not, for example, type check the code. Is it because you rely on the symbol caches, for example, for stuff like this?
So the type checker we use is different. It's very similar, actually shared source from the one in the compiler, but it tries its best to produce results even in the face of mangled inputs of any kind. And so by and large, if mistakes are localized, then we still have partial type information. And we can even do the rest of the build, as it were, even in the face of errors lower down in the import graph. So we try to always, GoPlease, we assume that the source is broken all the time because you're normally in the middle of editing. So we do our best. One more question?